I'm responsible for delivering Kubernetes clusters to customers and preparing configurations for these clusters. But for my job, I need to know how to deploy the clusters, and I need to know the application as well. So one part of my job is that I'm working as a Python developer in a different company to get something like a developer knowledge. And I would like to know the problems even from the other side of Kubernetes clusters. And I think last year at LinuxDays, I was speaking exactly the same room, but in the time I was working as an infrastructure engineer here at the Faculty of Information Technology. So Jakub has already given us some kind of introduction to containers and to Docker and similar stuff. And now I'd like to give you some way how to get from Docker to Kubernetes. First of all, I was planning to do this talk, something like a real production use and hard Kubernetes users. And I was expecting that I will say everybody already knows Kubernetes, so we'll start with something more advanced. But then many folks came to our booth. We have a Kubernetes booth outside, and we have a still cake in here. If you will answer the question, you will get a cake, because we are celebrating Kubernetes release 1.8. Back to the presentation. And then I decided that I would need to give a little bit more introduction to Kubernetes, even for the beginners, because I'd like all of us, you to get something for you, and I don't want to start from high-level Kubernetes. So I will quickly show you the differences between the Kubernetes and the Docker. The main difference is that we are not working with containers directly anymore. We have something called pod, and the pod is like an abstraction in Kubernetes. I'll be speaking about it later. And so we don't touch containers anymore. We'll create the pods, and these pods contains containers. These pods are basically built by the containers. And another difference is that for the networking, we need the communication between the pods on different hosts. If you start the containers in like a default Docker, you will have something like a random IP addresses for the containers. But if you will start another containers on another Docker machine, then if you are using default Docker networking, these two containers or different machines will not be able to communicate. But for Kubernetes, it's a cluster solution, so we need each container to be able to communicate with any other container. There is some small problem that in big companies they usually have some requests for like a segregation of the network or splitting it on parts. But I will be speaking about like a upstream version of Kubernetes, like a default deployment. And another difference compared to Docker is that we don't say how to run the containers. We just define the desired state, like how many containers should be running and how they should be connected together. And then we wait for Kubernetes to prepare it for ourselves. I'll be speaking about it later as well. This slide is here to ensure that we know what we are speaking about, because Kubernetes use like a different terminology for the resources. So I will quickly go through these resources to be sure that everybody will understand what I'll be speaking about in the next slides. So the node is basically the machine which is running the container. Docker or any other runtime is installed on this machine. The pod is the group of the containers. I was already mentioning it before. So for the simpler solution, you can think about the pod as a container, because the pod can have one container. So it can be basically the same. It's a little bit more complicated. We can speak about it at the end of the presentation. And then we have something called replication control or deployment or whatever else. And it says how to run the containers. Then on the next slide, I'll explain it more deeply. Then there is a problem which needs to be solved, that every time you will start the pod or the container, it will get something like a random IP address. So you need to provide some routing from your like a fixed IP address to this dynamic IP address of the pod. So that's the reason why we have services. And these services are basically ways how to forward your traffic to the containers directly. Then we have a persistent volumes and persistent volumes claims. And these are used for setting persistent volumes in a container, settings like a permanent storage. It will be really nice to run only the stateless applications in Kubernetes, but almost every real application on some part of the application need persistent storage. So persistent volume and persistent volume claim is the way how to add the storage to the containers. So, and in this picture you can see like an abstract architecture of Kubernetes. We have some definitions of the pods on the containers, and there is something called Kubernetes master in here. It's a little bit more complicated. I will explain the Kubernetes master as well on the next slides. But for this simple example, you will show the containers. You will describe how they should be running. Then you will get it to Kubernetes master, and it will somehow calculate or schedule these containers and run them on the nodes. You can see that I have not supplied any information on which nodes exactly it should be running. Kubernetes will take care of it and will do the best to run the infrastructure the right way. And Kubernetes itself is basically the scheduler for containers, and it can provide you like more features like storages and advanced networking or storage, secret management and this kind of stuff. But in the end, everything in Kubernetes is only the YAML. If you'll be managing it by yourself, like manually, you will take these YAMLs and apply them to the Kubernetes master, and it will try to do the best to run it exactly how you defined. In this simple example, you can see that there is a deployment. I define that I want to have 3 replicas running, which means like 3 pods. And there is an image which should be running in here, and I'm passing some secret. This is the same demo which we are running on the booth. You can take a look at it, or we can take a deep look at this at the end of the presentation. I will try to make the presentation a little bit shorter, so we will have enough of time for asking the questions, or if you will have any questions during my presentation, or I will make any error in my presentation, just don't hesitate to raise your hand and ask me. And you can see that I'm not defining any IP address or anything, whatever here. So now we have described what is the basics of the Kubernetes, and now let's move that you got a request for Kubernetes. You need to install it somehow. So there are different ways how you can install a Kubernetes, and it depends on your use case. For example, these Minikube or PicoCube are the installers which are used mostly for development. If you want to run it on your developer machine or in really small and easy deployment, you will use Minikube or PicoCube. If you want something like upstream supported or like a simple tool upstream supported, you can use kubeadm. But I think that kubeadm still can support multi-node deployment, so it's quite hard to bootstrap it. And then there are other deployment tools used for, it depends on which configuration management you like. For example, the kubespray here is based on Ansible. I'm developing salt formal Kubernetes. We are using this salt formal for deployment of our clusters. And there are some hosted solutions like Google Container Engine, which works something really nice. You will just click and you will get a Kubernetes. No need to install it. On the other hand, it's a little bit more expensive. Oh. So it seems like we have another presentation. Yeah. And at the end of the day, I think that it really doesn't matter which tool you will use, because Kubernetes itself is really simple, And only thing which matters is the configuration. And you can usually set any configuration with any tool listed in here. And another thing which matters is the architecture. How you will connect the Kubernetes resources or how you will be running it. And the thing which is really hard is LCM, which stands for Lifecycle Management. It's like how I will update my Kubernetes and how to update it without any service interruption, or how to make rolling updates, or what to do if my upgrade will fail or whatever. So for the LCM and all the stuff, quite common request is we need HA, like high availability for everything. And we need to have 100% running all the time. Yeah, it's possible to do it with Kubernetes, but you really need to think if you really need it, because it will complicate your architecture a lot. And it depends which kind of HA do you need. If you need HA for an application, that your application will be running most of the time, even with some hardware errors, or if you need HA for control plane, like a control plane of the Kubernetes, so the Kubernetes will be running most of the time. Or if you need HA for storage, so it means like your storage will be running all the time, even if the power will go down. So for example, if you are running simple NFS server, you don't have an HA for storage, probably. Or do you need HA for network? So if part of your network will go down, is your application still running? Or do you have HA for uplink connections? It really depends which HA you want to provide. Kubernetes can be built in really, really huge clusters with these nice features, but it will bring you more complicated lifecycle management at the end. And only thing which depends and which defines how you want to run the Kubernetes, it's your workload. You can have different applications running, and you can have different requests for the type of your services. For example, if you have dynamic application, it means that you have a high rate of pod churn. It means that you are starting and stopping containers very quickly. Or you can have a static application. So you will spin up your containers, and they will be running until they will die, or your hardware will die, or whatever. Another option how to decide on your workload and on your architecture is if you are running stateful application or stateless application. Stateless applications mean that you don't have any storage, you don't have any state stored inside, you don't have any cache. You have seen it, I haven't touched it. You don't have any cache or whatever. And these applications are really funny to use. These applications are really funny to run them because it's really easy, you don't need any storage or anything else. On the other hand, we have stateful applications, so you are storing some data or state or caches or whatever else. And for these applications, you need some kind of storage. For example, if you're running a database in Kubernetes, you will probably want your database to be running and have your data even after restarting the pod on the other node. Another thing which is necessary to decide if you have multi or single worker applications. For single worker applications, you've got a problem because your single worker of the application is like a pet. You don't want it to die, and it should be running all the time. And you shouldn't be restarting it and doing anything with it. So forget about the migrations. No, your application should be running all the time, and you will never touch it. And on the other hand, you can have multi-worker applications, and these applications are running in many replicas. So it's quite easy to kill a few of the replicas and start the new replicas on different nodes, or like one by one move it to another node. So it's really better, and it can use like this Kubernetes cloud native stuff easily, but only with the multi-node applications. And you need to think about these questions before you are creating the architecture for a Kubernetes, because it basically describes your requirements or your desired architecture. Yes, for sure, you can build Kubernetes which will be able to run any application, but it will be really expensive. You will have a lot of load which will be used by the services which shouldn't be there, and it will make your application much more complicated. So it will be much more error prone. So you can make any error by basically administrating the applications. Sorry, but it's still in here. So please, every of you, can you go here and look at my computer? Yeah. Sorry. So it makes sense to make your cluster as minimal as you can have. For example, if you want to have a cluster supporting everything, every other application, then you will have to pay a lot for cloud architect to design these huge silly clusters. So Kubernetes itself is fairly flexible and can be running in many ways. And these applications can be, this is like a microservice by itself. So each of these control plane daemon is doing only one thing usually, and it can be like replicated for different types, and I will explain how they are replicated. Actually, the most important part of the Kubernetes is not the Kubernetes itself, but it's the etcd daemon. And this daemon is the only component which is storing the state. And you need to be careful about it and don't let it die, because if your etcd will die, and this daemon is storing everything in Kubernetes, so you don't have a Kubernetes, it's basically dead. It's like a half of the Kubernetes. Second most important daemon is API server. And this API server is basically managing all the resources. And this API server is connected to etcd. And this one is only one daemon directly connected to etcd. So you need to have your etcd running and API server as well. Good thing about the API server is that it doesn't store any data by itself. Everything is in etcd. So you can run like 5 of them or 3 of them. You usually run like only 3 of them. If you have really huge clusters like 200 nodes and more, then you will be running 5 of them. And there is a configuration option which you need to set, and it is how many of API servers are you running. And all these API servers, for example, if you are running 3 of them, all these API servers will be in active mode. So they will be communicating with each other using the etcd. You will probably have 3 of them like this way. And another daemon is a scheduler, and this daemon is responsible for assigning assigning pods to the nodes. Basically, it will decide where you want your containers to be running. And this daemon is connected to API server and waiting for new requests. If you will not be starting new pods, it will be just waiting. But this daemon itself is doing the decision where the container should be running. And this decision can be like a random. For example, if you have 5 nodes, 5 physical servers, and all of them are fine for a pod, for your container, then it will decide which one is the best one and use it. So that's the reason why you cannot use multiple schedulers. So you can run multiple schedulers, but only one of the scheduler will be active. So this one is inactive, and these ones are waiting for the primary one to die. If the primary one will die, basically the daemon will stop, and the next scheduler will become active, and it will become the primary one. And the same for a controller manager. And this controller manager creates resources in Kubernetes, like, for example, if you will create a deployment, it will create the pods for you. I will be speaking about the deployments later. And the controller manager is running in the same way as a scheduler. Like, one is active and the others are waiting. Another important, and all these daemons are usually running on something which we call Kubernetes master. That's the heart of the Kubernetes, like a control plane. You can imagine it as the driver or the pilot in a plane. There's the daemons which are managing all the Kubernetes cluster. And then we have the daemons which are running on the nodes and managing the containers itself. And this daemon is called kubelet. And kubelet is responsible for listening on the API server and checking if there are new containers which should be running on the node. And you can have only one daemon running on each node. And there's a funny thing that the kubelet itself is not able to connect to multiple API servers. So it has only one IP address to connect, which is not very convenient. Just imagine there is an IP address and only one. If this API server will die, the rest of the Kubernetes will be fine, but this kubelet will be screwed because it doesn't have any connection. So that's a funny thing, that for like a production use, you still need to have something like a load balancer between your API servers. So the kubelet is connecting to load balancer and not directly to API server. I really don't know why they don't implement this feature like switching to another API server, but it's still not merged in the master branch. So I think that it will be never supported. And the last daemon is a proxy. And the proxy is running in the same mode as a kubelet. It's running on the minions. And it basically set your IP tables to forward your traffic into the pods. Yeah, sure. Mm-hmm. Yeah. etcd itself is able to make a synchronization between them. So there are 3 of them running, like usually on 3 different hosts, and they are running synchronization between each other. It's a really nice thing about etcd. You need to supply only the other daemons, and they can connect together, or there is some auto-discovery feature. So this is really 3 of them running. This service is really nice for this, like, yeah, the API server is able to connect to multiple etcd, and it will be switching. Like, it will select the first one, and if the first one will die, it will switch. You don't need something like a load balancer for etcd. And it's not recommended because it will make your etcd slower. Any more questions? Fine, thank you for a question. There is a simple picture that I have already created here. It describes how the daemons are running. You can see here simple single node control plane, and you can see dependencies between the services. As I have already mentioned like a million times, there is an etcd, and only API server, usually, is connected to etcd, and other servers are connected to this API server. It's basic REST API, so it's really nice and quite easy to write your own daemons or watch for the states inside your cluster. However, this is like a easy architecture. If you need to have like more daemons, it will be a little bit more complicated. Oh, sorry for the green one. There is a green part of the server, so I will read it for you. You can see here that I have three servers. There is 1, 2nd, and the 3rd, and I have an external self-storage. Still, there is only one control plane, one API server, and all the daemons, and it's still a little bit more complicated than the picture before. And if I would like to have like a real solution, I will probably be running these servers or these daemons on the other nodes as well to have 3 of them. It really depends how much redundancy you want to have. You can, for example, you can be running only 2 schedulers if you are fine that If one schedule will die, second will be working, and you don't expect second to die as well. But for example, on this picture, you can see that I don't have HA for a network because I have only one proxy, and this proxy is forwarding a request to all the hosts. Usually, the biggest problems are with storage and the networking. We have already solved the compute problems. We can schedule containers and run in many runtimes or many C groups or whatever. So compute is quite fine, easy, and quite cheap. But the problem is with storage. So because the Kubernetes is really dynamic environment, you can start your new containers, and containers will die and start a new one. So you need to have your storage dynamic as well. For example, if you will be using some kind of storage, you will probably want this storage to be able to create volumes on its own. So if I will start a new containers and I will request the storage, I don't want to create this storage by my own, like manually, or mount like iSCSI volumes or whatever. I want Kubernetes to create the storage directly for me. So there are some requirements for the storage to be used in the Kubernetes. And the basic one, that the storage can be mounted on any minion, anywhere. Yeah, you can just change all the settings and mount your storage only on one node and make all of your containers to be running on this node, but it doesn't make sense for a Kubernetes like itself. And another request is like, do you want to have dynamic provisioning of the volumes? It's called the storage class provisioners. We can talk about it later, but it's like for 2-hour talk to speak about every provisioner for storage class. From my point of view, probably the Ceph is the best solution for on-premise deployments. It's really dynamic, and it has really nice support in Kubernetes. And you can be using Rados block devices or Ceph, so it's up to you. But from my point of view, this is the only real high available Ceph storage for Kubernetes. There is support for whatever you want, like NFS and mounting even the host volumes or whatever else, but Ceph is probably the nicest one. On the other hand, it's really expensive to run it and build it. If you'll be running Kubernetes on like cloud providers, you'll be probably using like AWS Elastic Block Storages or Google Compute Platform Disk. Is it platform? Probably, yeah. Google Disks, and Kubernetes is able to manage this for you. Yes, it's still really nice and works like a charm, but be expected to pay for these disks, for sure. And if you don't have any other solution, you still can have an NFS server mount this export on all the nodes and use host path, but you need to be sure that your NFS server will never go down. If your server will go down, or your IO operations on the containers is stuck, and your Kubernetes basically is down and nothing will work. And another most expensive thing in cloud whatever is a networking, because you need to have really different requirements than we used to have before. For example, for Kubernetes, we need to have networking between the pods, like between each container on any host. And another problem is that we want to have some way how to route your external traffic. Like, for example, if somebody is accessing your web page or whatever, you need to forward these requests to your applications. So, and you need to have your networking which is able to do it. It's able to do it in cloud native way. So it will understand the Kubernetes, and for sure you want to make it as fast as possible. There are basically two solutions. You can have overlay network or underlay network. Overlay means that you will take your old network and build something like a tunnels between each nodes. So you are building new network in your existing network. Or you can use non-overlay network, not underlay, but non-overlay network. And it means that you are integrating your Kubernetes in your existing network. But your network should be able to handle many changes in IP addresses and all the stuff which is provided by the Kubernetes. So there are different ways how you can do it. Basically, like forwarding your request to pods. But if you will be ever building it, please don't use cluster IP for customer traffic. Yeah, we can use NAT, then we will end up by using NAT on both sides, so you'll be doing NAT even into the internal network. But probably the best solution is to have a load balancer or an ingress controller. There is some small problem with load balancer. You need to have an external one. Kubernetes will not provide it for you. On the other hand, you have support for all the cloud drivers like AWS, OpenStack, or any other. So Kubernetes will automatically configure a load balancer for you. And you don't have to care about it, and it will be like a native one. No other additional work with it. But you need to have this load balancer. And if you have really huge need for dynamic microservices, mesh networks or whatever, then you can use other tools like Istio or Linkerd, which are basically used to connecting your microservices together, do some advanced traffic inspection and all the stuff. So this is how the easiest Kubernetes networking works. There is output from the internet or the customers or whatever. This Nginx proxy is basically the ingress controller. It's something which is able to configure itself by the Kubernetes. So it will read what are the addresses and it will configure itself. Then we have a kube proxy, the daemon running on each node or anywhere in a cluster. And then we have the pods. So your traffic will go from the outside to the first proxy, to the second proxy, and to the nodes. Yeah, there are two proxies. Some like web guys don't like it a lot because it makes your requests much slower. On the other hand, you have a horizontal autoscaling here. It's on vertical, but it's scaling horizontal. So you can horizontally scale your infrastructure and make it a little bit faster. There are ways how to do it without these proxies. For example, if you are using container networking, there are direct tunnels from the containers into your, I don't know, core router. You can do it any way you want. Question if you really want to do it this way and if you don't like these proxies a lot. Another funny thing about the Kubernetes is that it don't care about the images. You can run any images inside. Only one requirement that each node should be able to pull these images. So yes, you can use local images, but it's really a pain to use it. So just imagine that every of your nodes should be able to do Docker, pull, whatever name of your image. There are different approaches how you can manage your images. And it depends if you prefer diversity or the unification. If you are using same image, so you prefer the unification. So it's much easier for you to apply security patches on your applications. But on the other hand, if there will be security bug in the operating system itself, it can jeopardize your applications so quickly. And it's easier to manage it. And then another good thing is that if you are running same version of operating system in the containers and in the host operating system, you can be sure that your kernel and the features will match, which sometimes it's necessary to do it this way. On the other hand, you can prefer diversity. You can be using different images for the containers. You are free to use whatever you want, but it's harder to manage all the patches and all the stuff. And don't use like a historical releases like running Debian 5 on top of the latest Fedora, because you will have a problem with compatibility between the kernel and your system. And for Kubernetes, you will basically need the registry. This is the store where the images are stored. You can use like a Docker native one or Atomic Registry or any other solutions. And it is here for you to store your images, like your local store for images. And you will probably want have your images to be somehow audited. It's a really funny thing if we build the cluster for a customer and they will run the application inside, and we provide them with the tool how to read all the images in the cluster, and they will see this image. Oh, and this is a real problem because nobody have like audited this image. Nobody have studied it, and it takes quite a lot of time to explain them why this image is running in their cluster. So another part, which is quite important if you're running Kubernetes in production and you are expecting some special features, is that you need to tune it a little bit, because defaults are fine for most of the common cases. But if you request something like spin up containers really fast, or migrate them really fast, or if you are expecting to have a really dynamic cluster, like you will be spinning a lot of containers and they will be dying quickly. So it's wise to set these parameters. There's a link for a nice article about setting all these parameters. So for example, if you can set up how many of the memory will be API server using and all the stuff. And it's quite obvious. If you'll be running more containers, you will need more load, and you will basically get more load, and you will need more memory for your control plane and for containers as well. Another thing which is really nice about the Kubernetes, it's really simple. So it's really easy to start it and use it for a production, but one day you will decide to update it. So you need to have some kind of lifecycle management plan, how you will update the packages, how you will be doing Kubernetes upgrades and any other upgrades. Then we are going back that you need to know your workloads. You need to know if you can update the cluster and if you can request some downtime, or if you can have some short service disruption or whatever. So it needs to have an LCM plan. The bad thing about the Kubernetes is that it's so easy to install it. So, for example, if you are installing OpenStack, it's really much difficult. So you are somehow expecting the updates to be difficult as well. But for the Kubernetes, it's really easy to spin it up and start using. But updates are not so easy. And back to my first slides, it depends on your workload. Yeah, there are, as I was writing in this picture, only API server is accessing the etcd directly. It's not true, sorry, I was lying. And for example, if you are using Calico networking, which is like networking solution for distributing IP addresses of your containers between multiple hosts, this Calico is using direct connection to etcd as well. And you have a problem because you have an interdependency, and if your ATC will go down, which will make Kubernetes go down, and the Kubernetes go down means that you will not run any new containers. But your existing containers are fine and they are running easily. But if your ATC will go down and you will be using Calico, you have a problem on networking layer as well, because your Calico daemons will not be able to do any updates in your networking, which can be a problem sometimes. There are two additional like important parts of the Kubernetes installation is a registry, because you need to have your registry up and running all the time, because it will be accessed after starting new containers. If the containers images are not present on the host, it will try to download it, like a bullet. And another important service is DNS service, because this DNS service is used for discovery in like easy clusters. If you don't need any fancy microservice mesh, you are fine with the DNS service and Kubernetes will provide it for you. But this DNS service is quite slow, but it can be scaled really easily. So you need to think about it and scale it if you need it. And there is even the autoscaler in Kubernetes which can scale it for you, but you need to enable it. Another thing about the Kubernetes is that you have requirements for another services as well. For example, you need to have like intelligent monitoring. because your services will be running on unpredictable IP addresses. It can change the IP address for some time. You can add more Kubernetes minions. Your workload will be migrating if you request and all the stuff. So it's wise to monitor your applications and to monitor Kubernetes as well. For example, if your application, which can restart very quickly, it's pretty common that your application will, for example, run out of the memory. It will be killed by the limits or OM killer or whatever, and Kubernetes will restart it so quickly that you will not know that your application was restarted. It's usually not such a problem, but for some applications, you need to know that your application was restarted, and you will probably want to change the amount of memory assigned to this application. So it's necessary to monitor these restarts as well. Yeah, I'm quite happy that in my work, I'm working with non-production clusters. I will just design them, give them to customer, and I don't care about it anymore. It's a production, and I'm not touching it. So, but sometimes some customers will require something like a backup or whatever. So there are different ways how to backup the Kubernetes. Probably the most easiest one is to backup the etcd, because only the etcd is storing the state, and then somehow think that you will be able to recover it, and the backup Kubernetes configuration as well. But I think it's obvious that nobody will be doing manual changes in it, and everybody is using like configuration management, so it's already in Git or whenever you want. So backup the etcd. I'm sure that it doesn't make sense to backup all the virtual machines like a virtual disk of any system and whatever, because you will be able to easily recover it. So another approach is to just backup important namespaces, or backup persistent volumes, or can your storage do snapshots? Depends on storage you are using. You need to decide if it's easier for you to recover your application in case of it fail, like if the Kubernetes will fail, or if it's easier to reborn it, like spin up new clusters in a provider and put your workload back from your backup. It's a really good way to test it before your disaster. And the next slides are about how not to design your applications. Yeah, you really don't need Istio and Linkerd or any other buzzword services if you are running application with free containers. And to be honest, most of the applications are running in free containers. Maybe some of them are 5 of them, but it really depends what you are running in your cluster. So think if you really need it and if it's going to help you. So our company decided, not our company, that's like the fairy tale, like just imagine that your company has decided to run Kubernetes, hired some cool DevOps guys to install the Kubernetes, and okay, let's run everything in Kubernetes. Let's take Oracle databases and put them in Kubernetes. Let's take Windows servers and put them in Kubernetes. You know, there's a support for Windows in Docker. And yeah, don't do it this way. It doesn't make sense for most of the applications, like a legacy one. It doesn't make sense if your application is running one worker, eating like 16 giga of memory, and there is no point of running everything in Kubernetes. Run only applications which make sense and which can benefit from Kubernetes. Don't complicate your life a lot. I know it's usually not the problem of technical guys, but the managers will decide that they will be running everything in Kubernetes, but it's wise to fight sometimes. So, okay, Kubernetes is great. Let's take kubectl, which is the command for controlling the Kubernetes, and use my bash to parse the output of the Kubernetes, the JSON one, and we will do anything automatically. Please don't do it this way, because it will take me like 2 weeks to convert these bash to something like usable. Kubernetes is really nice because it has an API server, and it's a REST API. And there are clients for every possible language. So it's really easy to connect to this API and do this actions using the API. Even if you are an administrator and you are scared by anything like a Python or any coding, it's really easy to do it. Just try it and you will like it maybe a lot more than using kubectl directly. Any questions about these 3 important slides? Maybe they are the most important slides of my whole presentation. Okay, if there are no questions, I'll be on the Kubernetes booth. You can ask me anytime. And it's time for a demo. How much time we have? Like 5 minutes? Okay, it's great. Maybe we have maybe 10 minutes. So I have a really simple use case. Oh, I will switch my... Can you see something? No. I like common use case for Kubernetes is it's not real multi-tenant applications still. That's a pity, but main purpose of the Kubernetes is to spin up containers as easily as you can spin them. So at the end of the day, you will probably, sorry for the branding, I will put it away. This is an application called KQueen. It's open source on GitHub, but it was branded by some UI guys. So at the end of the day, you will end up with having multiple clusters, and probably each cluster will be used by the different team. So you will be like now we are used to manage virtual machines. Somebody will request virtual machines, and we will give it to them. After a few months, maybe years, I hope it will be not more than years, the people will request Kubernetes directly. They will request this access to API server, and they will not care how Kubernetes is running. Maybe you will have some ways if you want to have high HA or not, but it depends. At the end of the day, Kubernetes is like a commodity. Just give me my Kubernetes, I will use it. So I have this simple tool, which is, for example, able to deploy the clusters, but we don't have a time to deploy the cluster. And I'm not connected to VPN, so it will probably not working, but we can try it at the end. But I have a Kubernetes cluster in here. I usually just show the kubectl. Can you see something in here? Can you read it? Or at least some outlines? I try to make it bigger. Yeah. I have a Kubernetes cluster in here. And today I'm not going to show you kubectl, probably. We can come to back it later. But you can see that I have some list of the nodes. They are running in AWS. You can see my external IP addresses, like this way. Please don't DDoS these IP addresses, it's just a small instance. You can see the state of the instance, if it's disk and memory pressure and size. And on the right side, I can see how many pods is running in my Kubernetes cluster. Another important information is what is actually running in Kubernetes. You can see here that I have a Flask application in default namespace with three replicas. So this container called Nginx with this image is running 3 times in my cluster. I don't know where it exactly is running, but I probably don't care where it's running. So I have a Flask application and the Redis. And this part of the Kubernetes is used for our demo on the booth. And I have another system services like kubedns, DNS autoscaler, and dashboard or anything else. And then I have services. If you remember, service is something like routing or the way how to put my workload, like forward my requests to my applications. And as I have mentioned here, it's running on AWS. So I have native support for AWS resources. So my application is using Elastic Block Storage disks, and it's using Amazon load balancers as well. So you can see that if I will open it, now I'm routed to my Kubernetes cluster, and I can see output of it. if you have seen our blue, you can see that that's exactly the same output, and it have been shown like 2,000 times already. For sure, I can get same information by running kubectl and get, I don't know, all. I'm sorry, I have reused the cluster which was used for customer presentation, and it was in California, so this cluster is running in California, and it takes some time before I will connect it from here. But here you can see like more CLI people-friendly output, but it's showing exactly the same information. There is a free Flask application, some service with external address, and there are some silly stuff. I don't want to bother you with this one. So this is a way how you can easily manage the clusters. And I think that I'm running out of the time, so I will take the last one. The funny thing about the Kubernetes is that if you want to connect it, you need just the API server and you are here. So at the end of the day, you will end like me. I'm having like 15 clusters running somewhere. So I have 15 configurations for these clusters, like kubeconfigs. This kubeconfig file describes how I will be connecting these clusters. So it's really messy. And for my applications, I have implemented the storing these kubeconfig files. So you can easily request the file, and if you will be able to write all this data, download it, then you will be able to connect to my cluster. I have another cluster in here, which is really easier one. It's my local one running in here. You can see that I don't have any workload and I don't have any nodes because it's running on my computer. But the kubeconfig is very simple. I'm running out of the time, I think. So thank you for your attention. If you have any questions, just please quickly ask them just now, or then catch me after. We can speak about the Kubernetes all the day and all the night, and you'll see.